So I'll tell you about two-source extractors and resilient functions, and I'll define these so you'll know what they mean. So probably you all know how important randomness is in computing. It's used in algorithms, distributed computing, cryptography. Of course, for these applications, you almost always need uniform, uncorrelated random bits. So there are some lower bounds that if you want to do certain cryptographic tasks like bit commitment or zero knowledge, even if the bits are seemingly not that far from uniform, you can't do it. And of course, randomized algorithms, typically the analysis assumes perfect randomness. But natural random sources may be defective. Real computers often get their randomness from clock drift or thermal noise or some device like a Zener diode. And weak sources arise in other situations. For example, in cryptography, even if you start with some uniformly random bits, if the adversary learns some information about your bits, then conditioned on the adversary's information, your bits are weakly random. And these defective weakly random sources also arise in pseudorandom generators when you might be conditioning on the state of some computation. So it's a very natural and important goal to purify a weak random source. So now we want to model a weak random source. Your first thought might be, if you haven't seen this, you might think, oh, well, let's just use the Shannon entropy, which you're probably all familiar with. This turns out not to be ideal because the Shannon entropy could, for example, place very high probability, like 99%, on some fixed string, which is completely useless. And with probability 0.01, it's uniform on n bits. So this string has a significant amount of entropy, but you won't be able to do much with it. But with probability 0.99, it's useless. So it turns out that a better notion for this purpose is min entropy. And here, really what you're doing is taking the largest probability and taking the log of the reciprocal of that. So in this example, the min entropy is just a constant. But yeah, so let's talk about more min entropy. Here I'll use the notation nk source for a source on n bits with min entropy at least k. And what this means is that all strings have probability at most 2 to the minus k. So that's the way you should think about it. And a special case is we just have we have a set of size 2 to the k or more, and we have a uniformly random element from that set. This has min entropy k. And in fact, the general case, a general source with min entropy k is a convex combination of these special sources, so it's really enough to just consider this special source. So throughout this talk, a weak source is just think of a uniformly random element from a set of size 2 to the k. Okay, and our goal here will be to extract randomness from a weak source. So what we would want, ideally, would be a deterministic procedure to extract randomness from any nk source. We don't want our deterministic procedure to depend on the source. We want one fixed extractor and should work for everything, right? So our initial formulation might be something like this. We have some fixed deterministic function. Whenever this is a weakly random string, this is a uniformly random bit. Okay, but this is impossible. Excuse me. And the proof, it's not hard. If we had such an extractor, well, this deterministic function maps some strings to 0 and some to 1. It has to map half of them to one of these. Let's say it maps at least half of them to 0. Well, then this is a set of size 2 to the n minus 1. But the extractor always maps the output to 0. So it fails for that set. So this is impossible, this ultimate goal. So what can we do? Oh, there are a few ways we could try to circumvent this result. One is we could make some assumptions on our weakly random source. And this has been a fruitful area. We could define special cases of such a source where there is enough structure that we can achieve this. And this is a useful concept. But now let's say we don't want to make any assumptions on our weak random source. Well, one approach is to use seeded extractors, which extract using with the help of a short uniformly random string. So just an order log n bit string can help us do this extraction. But we're not going to take that approach here. Here we're going to extract using independent sources. So we're going to say, well, we can't extract from one weak source, but let's say we have two or maybe more independent weak sources. Can we extract from these two or more weak sources? And this can be perhaps useful in practice, right? If in practice you want to seed your generator, maybe you're going to use some operating system variables as one source and some unrelated variables as another source. Perhaps that would be useful in practice. But it's a very natural mathematical question. And that will be the focus of this talk. Okay, so in this talk, first I'll continue introducing the model, and I'll tell you about our results. And then I'll tell you some of the techniques we use, and then I'll conclude. Okay, so the focus is a two-source extractor. So here we have two independent weakly random sources, two nk sources. And we want one deterministic function that will output a uniformly random bit. Really, we would want more than one bit, but let's just focus on one bit for now. So in particular, we want the probability that the extractor equals 1 to be very close to 1/2. And there's a very natural matrix view of this. So I'll use capital letters to denote 2 to the small letter. So our goal here will be to construct a big N by big N matrix so that every big K by big K submatrix is balanced. It has roughly the same number of zeros as ones. So we could think of one weak random source as picking out some subset of the rows. Another weak random source is picking out a subset of the columns. And if you take a uniformly random element from each of these two sources, you get a uniformly random element from this submatrix. So if it's balanced, then the bit will be have bias. It will be close to 50-50. Existentially, we can do this with when k is just about 2 log n. Big K is about 2 log big N. So these are pretty small submatrices. But existentially is not what we want. Right? We want to be able to actually do that. We want an actual randomness extractor. So our goal will be to do this explicitly. So what can we do explicitly? So Shantan Vazirani first asked what we can do with explicit with two independent sources, and Shorn Goldreich looked at our model more or less. So what's been done? Okay, so going back to small letters, again, min entropy just log n plus a constant is enough. But what's been done? Well, Shorn Goldreich observed that the classic Lindsay's lemma says that a Hadamard matrix works for min entropy greater than n over 2. And that was the best known for quite a while until Bourgain came along in 2005 and used additive combinatorics to shave off a little bit. So 49%, 0.49 n. He gave some unspecified constant less than half. And Ron Raz also showed how to do it if he said you don't need both sources to have min entropy n over 2, but just one source could have min entropy n over 2. The other could have min entropy logarithmic. And this was the state of the art before our work. But then actually, because of because of the lack of success here in coming close to this logarithmic lower bound, people looked at extracting from more sources. So Brock and Pagliazzo Vigdorsen showed how to use a constant number of sources to extract from any linear min entropy. And then Rao showed actually min entropy even n to some small power is enough. And Lee, in several works, got it down to just 3 sources with polylogarithmic min entropy. So this is a very nice result. It's a great result, but you can't view it as a matrix anymore. Now it's a 3-dimensional object. So so 2 sources sort of seems special. So in our main result, we succeed in building a 2-source extractor for polylogarithmic min entropy. So this is sort of what happened before us. We got it down to just polylogarithmic min entropy. And we could extract just 1 bit or maybe a few. But Lee showed how to build upon our work and extract most of the entropy out. And this has applications to Ramsey graphs. So a K-Ramsey graph has no independent set or clique of size K. A bipartite K-Ramsey graph has no bipartite K by K clique and no bipartite K by K independent set. And Erdős, in maybe the first use of the probabilistic method, showed the existence of K-Ramsey graphs when K is just about 2 log n. But again, we were interested in explicit constructions. So pictorially, what we want here is we want to 2-color all the edges, say red and green, in such a way that if you look at any 2 sets of size k, if you look at all the edges between them, approximately half are colored red and approximately half are colored green. And there's been a lot of work. I won't go through this in detail. Again, the Hadamard matrix gets us easily to square root n. Then it was a breakthrough when Frenkel and Wilson got it down well below any polynomial, although it didn't work in the bipartite setting. Bipartite is harder. And then, so in bipartite, just getting below square root n was interesting. And then Brock et al. got it subpolynomial, and Brock et al. Again got it even lower. And then, and what we do, and was done independently by Cohen, is to get 2 to the polylog log n. Okay, so we can get Ramsey graphs, bipartite Ramsey graphs, where k is 2 to the polylog log n. Okay, so those are our results. Now let me give you an overview of our techniques. Yep, feel free to ask questions. Okay, so let me give you a couple of the tools that we're going to use. One is a strong seeded extractor. So a strong extractor, so X will be the nk source. So the first n bits are from a weakly random source. And Y, the seed, is going to be a uniformly random string. So D, think of D as much smaller than n. And a strong seeded extractor has the property that sort of even conditioned on the seed Y, the extractor output is very close to uniform. So an equivalent way of viewing this, which will be useful for us, is the following. If we cycle over the seeds Y, we get 2 to the little d different functions. So I'll call that capital D. Right, so we have capital D functions f sub y. So we think of each of those as just a function on the n bits. And for any weak random source x with min entropy at least k, most of these fy of x's will be close to uniform. Okay, for different x's, we'll have different of the fy's being close to uniform. But for any x, most of them will be close to uniform. So that's what you should think of. We have d functions, and most of these are extractors for any x. And there's an explicit construction where little d is just logarithmic. Okay, and don't worry about the number of bits, but just think of little d is logarithmic, so big D is polynomial. Okay, so we have a polynomial number of functions which extract, most of which extract from anything. There's been a lot of different work on this. So that's one ingredient. Another ingredient is a resilient function. So this is a Boolean function with the following property. So think of an adversary as controlling some number of the coordinates, q coordinates. This, we don't want the adversary to have much control of this function. What happens is that the remaining coordinates are chosen uniformly at random. So what we'd like is this function to be fixed when all of the remaining coordinates are chosen uniformly at random. Then the adversary no longer has any power. So that's what this is. It says the probability that a function is fixed on uniformly sampling the remaining coordinates should be very large. So the adversary's influence is sort of epsilon. So as an example, think of majority. If an adversary controls less than square root n of the coordinates, then if the other coordinates are chosen uniformly at random, well, you're likely to have a square root n deviation, and these n to the 0.49 adversarial bits are unlikely to affect the value of this function. Or as a negative example, think of parity. Parity is terrible from this point of view, because even if the adversary controls just one bit, the adversary has complete control. Again, we're thinking of the adversary as acting last. The adversary sees what happens with all the rest of the bits, and then the adversary can completely control the function. So this is what a resilient function is. You might think majority is the best. That might be your first thought, but it turns out there are better functions, and we're going to need these better functions.
Constant?
Sorry?
Constant function is much better.
Oh, yeah, okay, good. Right, there's the constant function, but we're also going to want a balanced function, a function that's approximately 50-50. That's a good point, because actually achieving the balance isn't as trivial as you might think. Okay, so let's start with a preliminary attempt. So we'll start with a strong-seated extractor that works for our min entropy k. X is our nk source. And now let's look at all these d functions that we talked about. So we're going to cycle over all values of the seed, and just think of our extractors outputting one bit. Let's not worry about that. So we have these big D bits. Most of them are good. Most of them are close to uniform. Well, if we have these most are close to uniform, well, maybe let's just, okay, yeah, the bad bits can depend on the good bits. Okay, if most are close to uniform, let's just try taking the majority. But of course, this doesn't work. I mean, we can't even hope to have a one-source extractor, right? But this doesn't work. The uniformly bits can be arbitrarily correlated. That's one reason. There are a couple of reasons this doesn't work, but that's one reason. The uniform bits can be arbitrarily correlated. What I told you before was assuming the uniformly random bits are independent. So that brings us to another tool that we're going to need, called a non-malleable extractor. This is a strengthening of a strong extractor. I'm not going to define it completely. I'll just give you a corollary. The corollary of this definition, okay, so the first property is what we saw before. We have these big D functions such that most of them are uniform. The new property is that not only are these a lot of the bits uniform, but those uniform bits are actually t-wise independent, almost t-wise independent. Okay, so now we are able to get this long string where the good bits are almost t-wise independent. T is small. Yeah, we're going to, I mean, right, we're going to choose, think of t as polylogarithmic. So they're explicit. So in a very recent result, there's this beautiful result by Chattopadhyay, Goyal, and Lee that says we can take the C to be just polynomial in t, just t squared and log squared n. And the min entropy can just be polylogarithmic, and then they can build these non-malleable extractors. Okay, so this is going to be an important tool for us. So this leads us to our second attempt. So let's just replace, let's just replace our the previous idea, but now use a non-malleable extractor. So again, so this is the same thing. Now we're just using our non-malleable extractor and cycling over all possible seeds. Okay, this is actually quasi-polynomial and no longer polynomial, but let's not worry about that for the moment. Okay, now we try taking a majority. Well, this doesn't work either. The number of bad bits is more than square root d. And again, this is not surprising because we only have one source. We can't expect to have a one-source extractor. But this is our approach is related to this. So the first step of our approach is to use our two sources to construct a string z on a polynomial number of bits such that almost all of the bits are uniform and polylogwise independent. Okay, so we're going to do something almost like what you just saw. And our second step will be an explicit extractor for z. And this will be something like a resilient function.
So I'm a bit confused. You're using two sources to construct this z, but you said the problem before was that you had more than square root d bad bits, right?
Right.
And here you still have much more than square root d bad bits, right? So what's the advantage of using the second source?
Okay. Yeah, the error is going to be a problem if we just try to use one source. So using two sources enables us to get much better error. So let me, okay, so actually it might be the next slide or two. So let's look at step one. Okay, so we're going to do what we said before in the beginning. We're going to apply the non-malleable extractor. Right, so if you look at, so here in this non-malleable extractor, the number of bad indices is some epsilon times d. Actually, it won't be, this is going to be too many bits for us. It's going to be bigger than d to the 0.99 or anything. But what we do now is we're going to sample some pseudo-random subset of these indices using the other source. So we're going to, okay, let's see, there's another picture. So T is some pseudo-random subset. We're going to do this pseudo-random sampling of this string D, of this string. This pseudo-random subset is done via extractors themselves, but let's put that aside for a moment. And we're just going to look at those bits. And the point now is that the number of bad indices becomes much more favorable to us. So why is that? In the first, if we just use one source, the fraction of bad indices is very small, but we have quite a long string. Now we're able to more or less maintain the fraction of bad bits, but get a much smaller string. So if we have a much smaller string with the same fraction of bad bits, this is a much more favorable situation. So that's intuitively what's going on. So that's a rough idea of what's going on here. But I don't want to spend too much more time on this because actually this step can be achieved in an alternate way just by slightly modifying a construction of Lie. But this is, a way to do that. So I want to spend most of the time executing this second step. So what do we have in the second step? We have this string z. The number, let's say it's of length m. The number of bad indices is like m to the 0.99. And the good bits of z are polylogwise independent. And let's call this distribution D. Okay, and this is what we want to extract from. We want to extract from such a string where the good bits are polylogwise independent and the number of bad bits is like m to the 0.99. And we're going to extract from this by using some sort of function. We'll think of it as a circuit C that we'll design explicitly. And what we're going to want is that when we sample the good bits x, we're going to want the function to be fixed with high probability. Right? Because the good bits are going to be uniformly random, and polylogwise independent we'll see is enough to get what we want. We're going to want the probability that C is not fixed, that it's not fixed, to be small. The probability that it's fixed should be very high. Okay, so step 2 will have 2 parts. In the first part, in reality, we have polylogwise independent, but now we're going to try to assume that they're actually uniformly random and independent, not just polylogwise independent. So there are 2 ideas that are going to make this work. The first idea is it helps a lot if we assume that this circuit is monotone. Why would that be useful? Well, a monotone circuit, we can easily tell whether the function is fixed after setting all the other values. Right? Because, okay, so x sets the good bits. Now, to see if the adversary has any control, we just need to substitute in the all 0 string and the all 1 string for the remaining bits. If those 2 strings are equal, well, then since it's a monotone function, then it doesn't matter what the adversary does. It's still fixed. So it's only going to be unfixed if the all 0 string and the all 1 string give different values. Okay, so in that case, the probability that C is not fixed is the probability that C of x0 is different than C of x1, and we're calling that C prime. So that's the first idea for this part. And the second idea is to use a result of Braverman. This is Braverman showed in a remarkable work that if you have any AC0 circuit, meaning any circuit of constant depth and polynomial size, then it's fooled by polylogwise independence. So if we choose the bits from a polylogwise independent distribution D, it's the same as choosing them from a uniformly random distribution U. These probabilities will be very close to each other. Okay, so these 2 ideas, so let's put these 2 ideas together. Right, so if we put them together, we say that if C is both in AC0 and monotone, then the probability that C is not fixed is the probability that it's not fixed when x is chosen uniformly random. The probability when x is chosen according to D is about the same as when it's chosen according to U, because because it's really just saying we're fooling this new circuit C prime. The circuit C prime just has depth 1 more than the original circuit C. So if C was in AC0, then so is C prime. Okay, so it's enough to fool the circuit C prime, and Braverman tells us that polylogwise independence suffices. Okay. So because of this, we can assume that the good bits are independent and uniform. So our remaining task is the following. We want an explicit construction of a monotone function C in AC0 on m bits such that C is resilient even if an adversary controls m to the 0.99 of the bits. And this function should be almost unbiased. It should be approximately 50-50. And if we do this, then we're done. But this still seems, this is still a non-trivial task. We're going to construct such a function or circuit C by de-randomizing I-tie lineal. So let me tell you about I-tie and lineal's work. So I-tie and lineal gave a probabilistic construction of a function that's resilient to n over log squared n bits. So again, majority is resilient to like square root n bits. Right? If an adversary is smaller than square root n, it doesn't have much control. But if it's bigger than square root of n, it almost controls majority. What this is saying is it's a much better function than majority. Even if an adversary controls, less than n over log squared n, it still will only have small influence over the resulting function. Okay, so it's a strong result. And let's look at, let me tell you what we're going to do is modify their construction, because we can't just use their function directly. So their function is based on the tribes function. The tribes function is just a DNF on disjoint variables. So you could think we divide the n bits into tribes of size about log n, and if all the members in the tribe agree, then we set the function to 1. If any member of a tribe, if in all tribes at least one member says no, we set it to 0. Okay, so that's why it's called a tribe, but it's just a DNF. So it's an OR of ands of disjoint variables. And the itiilineal function, of course, a tribe by itself is quite bad, because if an adversary just controls all the bits of an and, it can just set all those bits to 1 and then control the function. So it just would need order log n bits to control the function. But the itiilineal function is just an and of about n tribes, sort of. Okay, these tribes. First of all, they're randomly negated, so some of the variables in them are negated. And the partitions are chosen randomly. And so in one partition might look like this. Another partition, the first tribe might be here, here, and here. Right? So these tribes, the partitions are quite different. The intuition being that if an adversary, tries to control some tribe, a few tribes in one or a few functions, it won't be able to control all the tribes in all the functions, or at least one tribe in all the functions. That's some sort of intuition. And again, this function is resilient to coalitions of size n over log squared n. But there are a couple of problems with this function. First, it's probabilistic, so if we just tried to de-randomize their construction, it would take exponential time. The second is that it's not monotone. I said there are random negations. So we need to fix both of these problems. Okay, so how are we going to de-randomize this? So the key ingredient will be to construct these partitions in a pseudo-random way. And we're going to use more partitions, actually. Not just n, we'll use a polynomial number. And we're going to want the following properties: that any small subset of 1 through n has a small intersection with most partitions. What does that mean? It means, what I mean by that is, we'll say it has a small intersection with a partition if it has a small intersection with any block in that partition. Okay, so for most partitions, the adversary shouldn't be able to have significant influence over any one block. Okay, and by a small subset, I mean size n to the 0.99. And this is used to bound the influence of the adversary. But we also need the bias, and for this we'll need the partitions to be sort of pairwise independent in the sense that the intersection of any two blocks should be bounded. And this will be used to bound the bias of the function. Okay, so these are the two properties we're going to want. So how are we going to construct these partitions? We're going to, again, appeal to extractors, seeded extractors. So we're going to look at a graph of a seeded extractor. Usually we think of an extractor this way. So these are going to, on the left side, we're going to put all the possible inputs to the weak random source. And on the right side, we're going to put all possible outputs. And we're going to connect a string here to a string here if some seed on input this can output this. So the extractor property usually says that if you look at a large subset here, it distributes almost randomly over here. But we're not going to look at it that way. We're going to take this alternate view as follows. We're going to think of it this way. If we pick any sort of test set on the right-hand side, well, if we have a fixed test set here, each string here gives us an estimate of the size of t. the estimate corresponding to this will be the fraction of strings that land in T. Okay, so we have a bunch of estimates for the fractional size of T. The set of bad strings will be those strings on the left which give too high an estimate for T. So the fraction of neighbors that intersects T is significantly more than it should, by more than epsilon. And it's not hard to show that, that if you have an extractor, the number of bad strings is quite small. And this is the view that we're going to need. So it sort of seems related because we're worried about strings intersecting a block in too many places. And here we have something that intersects the set T in too many places. But this doesn't look like a partition. We don't have any partition here. So we have to somehow use this to build a partition. So how are we going to do that? Well, let me show you how to convert a function into a partition. So here's a function from 1 through b to 1 through m. For each element in 1 through b, it maps to one value in 1 through m. So this corresponds to a set, 1 I1, 2 I2 through b IB. Okay, and think of this as our whole universe. So this is n. N is m times b. So think of one fixed subset here, which corresponds to a function. To make this subset into a partition, all we're going to do is start shifting, right? I'll just add 1 to all these values. And then I'll add 2, and then add 3, etc. All the way through m minus 1. So if we start with some subset that corresponds to a function, just si plus 1, si plus 2 through si plus m minus 1 gives us a partition of that whole space. And this is how we build our partitions from the sets. Okay, and these sets correspond to extractors. So 1 and then the extractor of x. So each node on the left-hand side will give us a partition. Because each node on the left will define a set as follows. 1, extractor of x1, 2, extractor of x2, b, extractor of xb. So basically the neighbors of each node x gives us a set, gives us a function of the desired form. And this is the way we build the partitions. Right, so the properties we require, we require that for any t of this large size, it should have small intersection with the partitions. And this is like the extractor property. So we get this from the extractor property. And the second property says we need this sort of pairwise independence. If you translate it into this setting, it says that the neighbors of some node x, if you add I, and you intersect it with the neighbors of x prime, and you add j, this shouldn't be too large, maybe 0.9 times b. And this follows if we use Trevison's extractor. So this is related to what Lee called a design extractor. It's some generalization. Okay, so those are some of the ideas. So the analysis, gets a little complicated, although it's not terrible. But we give a new way of analyzing I-tilineal. It's crucial in achieving monotonicity and de-randomizing. And let me just tell you a useful inequality that comes up in our analysis called Janssen's inequality. Maybe, usually if you say Janssen, then people think you said Jensen. But then you say, no, I mean Janssen. So what this says is that, let's say we start with T subsets of some universe U. And we pick each element in the universe. We choose a random set by picking each element in the universe with some probability P. then under some conditions, if the sets are small and they have low pairwise intersection, which is the kind of setting we have, then the probability that all the subsets don't lie in R is approximately the probability of the product. And this is the kind of thing that we need in our analysis when we analyze the bias of the function. Okay, so I won't go into any more details. Let me just tell you about some subsequent work. So first, Lee used our construction to give an affine extractor for min entropy, just polylogarithmic. An affine extractor means this is the case of a structured extractor where the source is just an affine subspace, a shift of a linear subspace. Lee also showed how to build on our work to get a larger output length, like 0.9 times the entropy. And Raghu gave an explicit resilient function that matches the I-lineal bound. And this also helps improve the constant in our polylogarithmic. We had like 74, and he has like 10 if you want constant error, or 18 for polynomially small error. So some open questions. Can we get to negligible error? Right? We have polynomially small error, but for cryptographic applications, you may want negligible error. Min entropy C log n. Well, actually, for negligible error, you're going to need bigger min entropy. But for min entropy, just C log n, that would be very nice because it would give Ramsey graphs with just where poly log n by poly log n instead of the 2 to the poly log log n. And maybe most intriguingly, are there more applications of our work, either the results themselves or the techniques involved? I think there should be. We already have several, and it's only been a couple of months. So that's it.
There's one question.
The problem determining the Ramsey number in general is still open. Is there some special case called NP complete? I wonder whether the techniques you apply here can be applied to solve the general Ramsey number problem.
Oh, so the question is about finding the Ramsey number. So I don't think it would be helpful in finding them offhand because our techniques are mostly designed towards constructing something that we know exists non-explicitly. So I don't think it would help us establish the limits of sort of non-explicit constructions, but maybe it does in some non-obvious way. I don't know.
Other?
David, once you extract polylog n bits, then you can extract almost 2k bits, right? I mean, so you don't have to go only to 0.9 times k.
Oh, right, but the error isn't small enough. Oh, it's not as strong. Sorry, when you do.
So you need it to be strong.
Yeah, right. Right. Yeah, there's this. Right.
We have one more question.
Yeah, my question is about the applications to graph theory. So you mentioned Ramsey graphs, but more generally, you might want to construct pseudo-random graphs in the sense that so you say you construct bipartite graphs, and you pick any subset X on the left, any subset Y on the right, and you would like to have density about 1/2 with a good error term for any X and Y of any size. Has there been any progress on this more general question?
Well, I mean, sorry.
Case where you ask about all or nothing.
Oh, well, that's Ramsey, right. But actually, our construction, maybe I should have made that clear. Right, an extractor does give the right number. Right, so an extractor, if you view an extractor graph theoretically, like think of the matrix view, it says exactly that if you pick a subset X and a subset Y, then you have the right number of edges between them.
Yeah, but maybe the error term isn't quite optimal. Maybe it is related to what you get.
Yeah, the error term is not optimal, right, but it's still, I mean, 1 over polynomial is still, well, I guess it would be 1 over polylog when you translate it to the size of the, yes, it's not optimal. We could do better. So So right, so improving, I think it's equivalent, if I understand your question, I think it's equivalent to just improving the error here.
Yeah, I think we'll have to keep other questions for later, for informal discussion.